Here's a real short calculus assignment. Section 4.2, numbers 39 to 42. Going to write some equations for tangent lines. That is something that is not going away. Probably you have figured that out now. So let's see, we got that at my x sub 0 point, e to the negative 1. Alright, so I'm going to do it in point slope form, of course. So my point is e to the negative 1, and when I plug that in here, the natural log of e to the negative 1 is negative 1, of course. Taking the natural log of something is like asking, well, what would you have to raise e to get this number? Well, what do you have to raise e to get this number? Well, that, of course. What's the slope? I suppose when you plug e to the negative 1, which is the same as 1 over e, into this, it flips it back over into being e. So the equation for my tangent line is y plus 1 is equal to the slope times x minus e to the negative 1. All right. What's next? Log of x, that's log base 10 of x, which is the same as 1 over the natural log of 10 times the natural log of x, right? And we're going to do this, write this equation for the tangent line to this at x equals 10. All right. So this is for the purposes of finding the derivative, rewriting it like this. Of course, that's just a number, 1 over natural log of 10 times 1 over x. That's the derivative of that. For the purposes of finding, well, I guess it's easy enough to see what it is here, what the point is. If you plug 10 into this, whether you plug it into the original version of this, which is just log base 10 of x. Of course, log base 10 of 10 is 1. What's this? That should have been a comma. And then if you plug it in here, you can see what's 1 over natural log 10 times natural log 10. That's also 1, because it's the same thing. And then here, my slope is 1 over 10 natural log 10. Right? And if you wanted to change that back to log base 10, it would be kind of consistent with the presentation of the problem to do that. I'll go ahead and do that just for practice. So if you wanted to change 1 over, if you wanted to change natural log of 10, that's the same as log base e of 10, right? Which is, if you think about change of base rule, so that's the log of 10 over the log of yes, that's what we're doing. So that is log base 10 of 10 is 1, and this is log base 10, which they're just writing as log of e. We can just check that with a calculator too. Always nice to see these things come true. So the natural log of 10 is that, and then what's 1 over the log of e. Oh my goodness, it's the same thing. So that means that here, when we found our slope, that this 1 over the natural log of 10, that's going to flip. Since the natural log of 10 is this, that would flip that back up to the top. So that's log of e over 10. So your tangent line, you could write, if you want to stick with the original presentation of things in log base 10, then it would be y minus 1 equals the slope times x minus 10. There it is. We're going to go back at the end of this video and make some nice graphs of these things. It'll be optional for you. Probably a good idea to watch that. Try doing it yourself. Number 41. What function do we have here? The natural log of negative x. What's the derivative of that? Derivative of that, natural log whatever, 1 over whatever, times the derivative of what's inside. Still just 1 over x. How about that? Okay. So, let's see. How about, what is the point? What's the point? Anyway, at negative e, so f of negative e is equal to 1, because the natural log of e is 1. So there's my point. I guess I wrote it as a point, and these ones I should be consistent and do that. So that would be negative e comma 1. And then when I plug my negative e into this to get the slope, f prime of negative e is 1 over negative e. And I'm ready to write the equation for my tangent line now. So y minus 1 is equal to the slope times x plus e. 42. The last. How about the natural log of the absolute value of x at x sub 0 equals negative 2. All right. Let's see. So that is my point, and the slope I'm going to come back to this in just a sec and explain to you why we keep seeing these absolute value signs. I'm not sure that that was explained to you somewhere else. If it was, then apologies. But I'm going to do it again, or for the first time. Not really sure. All right. There you go. Now, what's up with these absolute value signs? Let's talk about that first. So, you know, well, pretty much everybody knows, that if you have the function f of x is equal to the natural log of x, that the derivative of that is 1 over x. But there's a little bit of a problem here with domain mismatch. Let me show you what I mean. So you know what the natural log function looks like. You should. It's one of those ones. It goes through the point 1, 0. It comes charging up from negative infinity, and then does this. There is no horizontal asymptote. It continues to grow, although the rate of growth of this is one of the most tragic, sad stories in all of mathematics. it just flattens out, and by the time you get out to 10, the slope of it is 1/10, and by the time you get out to 100, the slope is 1 over 100, and it just creeps along. But it will get as high as you want if you're patient enough and let it go out forever. Okay, so that's what that looks like. Now, how about this? What does 1 over x look like? Well, we can graph it and kind of pretend that we're doing, curve derivative sketching here. Right here at the point where x equals 1, it would have a slope of 1. And then what are the slopes like here? Well, they're really, really, really steep positive. They're very, very big positive numbers. And then as you get out to here, they're less and less steep, like this. Of course, you know what? This is another graph you should be familiar with. Looks like that. But this graph has another piece. There we go. Sorry about that. So what do we do about this? The natural log function only has a domain where x is greater than 0. There are no values. This function is not defined for 0 and negative numbers. You can't take the natural log of 0 or a negative number. So here, of course, the derivative of this is 1 over x, and that perfectly matches up here, but this function doesn't have the same restriction. So there's two choices that we have here. We can either restrict the domain of this and say, okay, if f of x is equal to the natural log of x, then the derivative is 1 over x, but only for x values greater than 0. We could restrict the domain of that, and that would work just fine. But, on the other hand, would there be a way, like a more inclusive way, of instead of like getting rid of part of this, what if we expanded this and then had it match up to this? Wouldn't that be better, to be like more inclusive? And the easy way of doing that is, forget this, let's do this. Now, what is the effect of doing that? Well, we've seen this before. If you put absolute value signs around the inside of a function like this, what it means is when you try to plug in -2, you get exactly the same thing that you would have got, or that you did get, when you plugged in 2. Because when you try to plug in -2, for example, you get natural log 2. So you plug in -2. It doesn't mean that the point gets flipped over to here. You're still plugging in -2. You're just getting natural log 2. So you get the same thing that you got there. What happens when you plug in -1? You get natural log of 1, which is 0. So it just gives you a mirror image. Like that. Now let's just make sure that that does what we want here. Does this match up to giving us the slopes of this? It sure does. So here, for example, if the slope of this was 1, then its mirror image here would have a slope of -1. Bingo. And it does everything that we want. So that's better. Instead of restricting this, we expand this. And now everything's good, except for 0. Nothing you can do about that. Can't patch that, because it's not a removable discontinuity. Now, the other thing I was going to do is optional for you, but maybe if you, since this was a very short assignment, you want to have some practice driving your calculator, you could try to graph each one of these functions and its tangent line, but with the caveat, or with the added requirement or suggestion, that before you hit that graph button, that you set up a really nice window for it. That's what I'm going to try to do. Okay, so here, for this first one, I've got natural log x is my function, and my tangent line is y equals, we'll have to move that to the other side, -1 plus e times x minus e to the negative 1. How's that look? I think I typed everything in there just fine. Okay, now I'm not going to graph it yet. I'm going to go to the window, and I'm going to think about what would be a good window for this. So e to the negative 1, that's my x value. So let's see, that's about, e is kind of close to 3, so that's like about 1/3. So let's see, what if I did a window that had x values from 0 to 1? So I'm going to kind of be pretty zoomed in on my my point of tangency in the tangent line there. So how about in the y direction? The y coordinate is -1, so maybe if we just wanted to have things be fairly square, I could go from -2 to 0. I think that should be a pretty good window. Let's try that. Pretty. And this, I am still in this simultaneous mode, which is kind of nice for graphing this kind of thing. You can see the two things graphed at the same time. All right, I think that was satisfactory for that one. So how about number 40? That was log x, right? And here, my tangent line is 1 plus the log of e over 10 times x minus 10. I think I'm good there. So let's go back to the window here. The point of tangency is the point 10, 1. So let's see. For my x values, if I just wanted to surround these again, I could do 0 to 20. And I could do here 0 to 2. See what that looks like. And there it is, the kiss. And you could move the cursor around, and there you are at the point 10, 1, right in the middle. That's a nice feature of this. I think the default position for that cursor is going to be right in the middle of the screen, and we're setting it up so that point of tangency is in fact right there. All right, cool. 41, we have the function natural log of -x. And in case, per our discussion that we just had a minute ago about why the absolute value signs, you know what that function looks like in the standard window? Think about that for a second. You can pause. I'm going to go ahead and graph it in the standard window. So it looks just like the natural log function, except we flipped it over because of putting that negative in there. So we're getting just the negative piece, like what we were talking about here. But if you put the negative sign in there, you'll only get this piece. And it's even better than my graph, like the tragic nature of this, of the growth of this. That will get as high as you want it to, but look at how flat it is already. Oh boy, what a sad story. All right, so where are we making our tangent line here? We made it, let's see, our equation is 1 minus 1 over e. You could do that as e to the -1 if you wanted to. And x plus e. Okay, and let's see. So that's the point -e1. So -e, that's about -3-ish. So what if we went from, like, I don't know, -5 to 0, something like that. And then the y-coordinate was 1, so it could go from 0 to 2. Oh, here they come. The kiss. Right. What is the big deal with tangent lines anyway? Why are we so excited about these tangent lines? Well, among other things, as you know from section 3.8, if you're around here, then this straight line is a very good approximation for the function. Everything is locally straight. Did you know that the Earth that we live on is a great big ball? That's crazy. I hope there are no flat earthers among you. If there are, I guess I apologize if you're offended by me saying that, but I would just like to point out that you're wrong. Isn't it funny how like matters of science have become like associated with like, not that like the flat earthers are a political party exactly. There are so few of them, I think, but like with climate change and stuff, that somehow has been politicized. It is like so incredibly tragic because it has nothing to do with politics. It's our planet and science. So anyway, get off that soapbox real quick. Here we are with the last one, with the natural log. Now we can see it in all of its extended domain glory. You know where the absolute value signs are? You do, right? Right there. Math, go over to number. If you've got the fancy 84 and you've got it in math print mode, then it might actually look like absolute value signs. Mine doesn't do that. And, well, let's just look at that for fun in the standard window. We graphed it on the last page. It kind of looks like there's a sharp point there, but we know that that's not actually true. If you zoomed in around, like if you did window, let's see, let's just go from -1 to 1. Still can't really see the asymptote action there. So let's see. Did you know that you can get rid of your axes for a minute if you want, or forever, I guess? If you go to Format and you turn your axes off, you can do that. Let's see what it looks like then. Does it still look like a V? Well, I guess there's that little gap there. So we could zoom in even more around the axis and do like, I don't know, how about -0.1. Boy, doesn't want to do it. How about -0.01? Yours might be better at, your TI-84 might be better at doing this than my old clunky 83. And the other thing I could do is, there's all this empty space up here. I could go to my window. The Y max does not need to be 10. It could be like 1. A little better. Anyway, you get the idea. So the problem with this, just in case you're interested, the way that the calculator is graphing this TI-83, I'm not really sure how much the algorithm changed for the TI-84s. I think not much. What it's doing is, whatever you make the window, it's dividing this interval up into how many pixels there are, and it assigns each one of these pixels a value, and then it plugs it in and does the math, and it tries to make a dot at each pixel. So what's happening here is, when it's getting to this pixel right in the middle, where it looks like there's a gap, it's off the screen, so it's not connecting that, which is why it's giving us that little blank. So it doesn't know that there's an asymptote. The calculator doesn't know anything. It's a stupid machine. Let's see. If you wanted to, let's see what our mode is. There's also this connected and dot mode. So sometimes, like when the calculator makes asymptotes, like for example, if you graphed 1 over x, which is in fact the derivative of this, isn't it? Then Well, let's just do them both on the same screen there. Oop. No good in that window, sorry. Let's go back to our standard window. Do that. Interesting. So it didn't connect them. I find that quite curious because it's in connected mode. So sometimes the calculator will do that like spike thing where it kind of draws in what almost looks like the asymptote, but it's trying to connect negative infinity to positive infinity. So it didn't do it here. Interesting. Anyway, some stuff about graphing. And here, what we really want to graph for our last one is our last tangent line. So that looks like we have natural log 2 minus 1/2 times x plus 2. And let's see, we want the window to be centered around -2, so how about -4 to 0? And natural log 2. What's the natural log of 2? It's kind of like 1-ish. The natural log of e is 1, right? And e is like 2.71828, yada yada. So I think if we did a y scale from 0 to 2, that would be pretty good. Oh, my axes are still turned off, but that's okay. There it is. So anyway, that whole flat Earth thing that I got, the Earth is locally flat. I mean, you walk around here, drive around Rockbridge County, drive around Virginia, even the whole United States seems pretty flat, doesn't it? Because the local linear, or I guess it would be the local planar approximation for the big sphere that we live on is, in fact, a plane. So, not an airplane, you know what I mean. So let's turn the axes back on, and then we'll give it one last look, and then we'll leave this. All right, there it is. See you later. Whoop.